And with a little bit of going through this and thinking about it, it's actually pretty easy to do, and I won't go through all of that agony. I'll just say that after some manipulation, you should be a little worried about that. It's easily shown that what you get for an output is that it is the output voltage is proportional to the input voltage, and the constant of proportionality is given by the ratio of R2 to the sum R1 plus R2. It turns out we have derived this in general, right? We don't have specific resistor values, we've derived this in general. So anytime you see a voltage source attached to two resistors in series like this, you'll always find that the voltage across a resistor obeys this rule. And in fact, I'm going to ask you to tell me what is the voltage V1. And I want you to do that without doing any calculations. I want you should be able to just tell me what that answer is. All right, well, that relationship that for voltage across a series connection of resistors is called voltage divider. The resistors split the voltage. Divided is where the terminology comes from. So the bigger R2 is, the closer the ratio here is to 1. The smaller R2 is relative to R1, the smaller this proportionality constant gets. So what does our circuit do? So remember, what we're trying to do is build systems, and we're trying to build them at this point out of circuits. So in terms of block diagram models, we have a source that's producing some voltage Vn, and there's the source is literally the voltage source in this circuit. The system is the entire circuit it's attached to, and we have taken as an output the voltage across R2. And what our system, the input-output relationship we have shown is given by that expression. So what does our system do? Have we encountered a system like that already? And the answer is we certainly have. It serves as a kind of amplifier. The gain of our amplifier is simply R2 divided by R1 plus R2. And because our gain has to be less than 1, resistors are always positive valued, it turns out we have an attenuator. And so what our little system, our circuit does in terms of system theory is that it serves as an attenuator. It makes voltages smaller. So let's do a little power calculation. I'm very interested in what is consuming power and what is the source of the power that's being consumed. So as we know, power for each element is the voltage that we have times its current. And I want to consider that for each element. So we know for a resistor that the power is the voltage squared divided by the resistance. That's V times I for a resistor. And since we solve for the output voltage, we might as well use this version of the formula. So what we get is that the voltage output, the output voltage, just to remind you, was R2 over R1 plus R2 times Vn. So you square that and divide by R2, you get that. And similarly, the power dissipated across resistor 1 is given by a similar expression where R2 is replaced by R1. I think that's pretty easy to see. Because these are positive valued powers, right? Resistors are always positive value, and we're squaring the voltage coming in. It turns out that means these two resistors dissipate power. They consume it. Well, it has to come from somewhere. So let's see what's going on with the source. Now, the output current is what we need. We need to find, we have the voltage V, that's just given by the source, and we need to find the current I that's going in. Well, for a series combination, I think it's pretty clear that I1 equals I out, and that I is equal to minus I1. So if I just find I out, which is given by the voltage that we found divided by R2, we know that that is I out, and I will be equal to minus I out, and what we get for a power produced by the source is the negative of Vn squared divided by R1 plus R2. And negative means it produces power. It is the one that is producing the power in the circuit. You add these two up, you add everything up, you get 0. And that's the way it should be. It has to be that power is conserved. There are going to be parts of a circuit that consume power, and there's going to be parts that produce it, and they have to be in balance, or there's something wrong with the calculations. And so no net power is produced or consumed by a simple circuit. And that's the way the laws of physics are. So, and this is the general formula that if you, for a given circuit, if you sum over all the circuit elements, the sum of the VK, IKs have to be 0. We'll prove that later. So, along with the VI relations, KVL and KCL always give you exactly the number of equations you need to solve any circuit. So you have to go through them all. And of course you don't need all the set of equations. What I mean by that, if they're an n-node circuit, you need n-1 KCL equations. And for a number of openings in a circuit, or only the number of loops you need for which you write KVL. Now, I do not want to spend my life solving lots and lots of sets of equations just to find an input-output relationship. So we really need methods to streamline our calculations, and we're going to talk about those soon. And it turns out they're very easy to use, and not only simplify our life, but give us insight into how circuits behave. Now, a little bit later, I'm going to prove that only KVL and KCL are needed to show that every circuit conserves power. The sum of the VK, IKs is indeed 0. That's really interesting, and we'll see that in a succeeding video.